Okay, so we're going to look at the factor theorem. So factor theorem is a very particular or kind of important theorem in algebra and to do with kind of functions generally. And when we're looking at the factor theorem, it is something that you kind of already would be familiar with, but maybe just wouldn't be able to write down explicitly or kind of fully explain. So we're just going to kind of make it really explicit, kind of write it down in its kind of, or state it, I suppose, in its kind of most exact form, and then we're going to see how that's useful to us. So the factor theorem basically says that if we have a factor, so like x minus a, if that's a factor of some function f of x, then that means that f of a is equal to 0. So that just means that a is a root. That just means that a is a root of the function. Okay, that's something we would already know. If you think of when you're doing your quadratics, you'd usually end up with your two brackets. So maybe x minus a is one of them, x minus b, and we would then write down x equals a, x equals b, okay, as our two roots. So if we have a factor, then if we were to take that factor, work it out as a root, and sub it into the function, it should be equal to 0. The converse of that then is if I have a value a, and I sub that into my function and I get 0, then that means that x equals a is a root, which of course then means that x minus a is a factor of my function. If I have then for ax minus b is the other kind of version that we could have, then we have that f of b over a would be equal to 0. It's just kind of an extension of that factor theorem. But what the factor theorem basically tells us, and that's what I'm kind of laying out here in the text part, is just that if we're given a factor of a function, then x equals a is the root, and we could sub that in and get 0. And similarly, if we're given the root, if we're told that x equals to a, and that's a root, then x minus a is a factor, and it should divide in evenly. And honestly, that's the key part that we're going to be making the most use out of for this theorem. So generally what happens is we try and find roots of the equation, and then from that we can find factors, and we'll be able to use that to factorize and to solve a particular polynomial. And it's often used with cubics, is what we're going to see a lot of the time, because we know how to do quadratics. We don't need to use this theorem to do quadratics, but we can use this to help us find one root and hence one factor of a cubic, and once we've divided in by that, what we're left with should be a quadratic, and we know how to solve a quadratic then. So that's what I've kind of said here. We can use the theorem to investigate whether a given algebraic expression is a factor. So let's investigate if x plus 3 is a factor of this particular expression here. So from our theorem there, if x plus 3 is a factor, so if this is a factor, that would mean that x equals minus 3 is a root. So if that is a factor, that means that x equals minus 3 is a root of that function, of that polynomial. So what I can do is I can sub in minus 3. And what I would expect if this is a root is that when I sub in minus 3 in all these points, that I get an answer of 0. That's what I'm expecting. So if I don't get 0, then it's not a root. If I do get 0, then that just proves to me that it is in fact a root. So the key thing here, I suppose, is just being able to work out all those parts and kind of know what you're looking for as well. Okay, so not alone that you're just kind of solving the question, but that you know exactly what you're looking for in each case. So we're subbing in our minus 3 here to all these points, and we're going to just make sure whether that gives us the answer that we're expecting. So minus 3 to the power of 4, that's going to give me 81. And then here I get minus 54, minus 225, plus 78, plus 120. So that's just solving all of those points or parts of the question there, and adding all that together we get an answer of 0. Okay, and 0 tells me that x plus 3 is a factor. Okay, so that tells me that I've subbed in the answer of x equals to minus 3, and since I've got an answer of 0, that tells me that that is a root, which means that x plus 3 is a factor. Okay, so as I was saying there, we can use the factor theorem to factorize and to solve higher order polynomials. So when we're saying higher order, we're typically thinking kind of greater than or equal to 3, so kind of bigger than cubics. So we're kind of thinking cubics and bigger. We know how to do quadratics and we know how to do linears, so cubics are kind of the first step that we're going to be looking at. So when we're factorizing these higher order polynomials, the first place we're going to use our factor theorem is in this first step here. We're going to use trial and error. So in some questions, they will give us a factor and we'll be able to skip this first step altogether. But in other questions, they won't give us a factor or they won't give us a root, and we have to use this first step. So we use trial and error to try and find a root of the polynomial. So remember, if we're finding a root, what we're doing there is we want to get f of a equals to 0 for some a, where a is the root. And what I've said there as well is when you're doing that, something to try is to try and use factors of the constant term. So if we're using factors of the constant term, oftentimes that will give us one of the roots of the polynomial. And it just saves us a little bit of time when we're just trying that trial and error. The other thing we can use, I suppose, is to use our calculator and fill in those values as we go. So it just saves us writing out every attempt that we're making. Once we've found our root, we need to rewrite that as a factor using our factor theorem. So as we've said here, if a was a root, then x minus a equals 0, and x minus a is a factor. Once we've found our factor, we're going to divide that into the polynomial that we're given. And as I say, a lot of the time this would be a cubic. So what the result would be a quadratic. And we're able to then solve the resulting equation to find whatever factors are remaining. So it's important, I suppose, to also know how many factors are you looking for. So let's just jump straight in. We'll just have a look at an example. It says fully factorize 3x cubed minus 19x squared plus 33x minus 9, and then solve the equation. Okay, then solve it equal to 0. So fully factorize first, then solve. So we're starting off with some trial and error. We're just going to try values. We're going to sub them in. We're going to see if they work out to give us an answer of 0. That's kind of what we're looking for at all these points here. So let's try, if we start with maybe x equals 1, I said we'd start maybe with factors of the constant term, and the constant term here is minus 9. So we could start with maybe 1, we could have started with minus 1, doesn't really matter. We're subbing in these values here. So I get 3 minus 19 plus 33 minus 9, and that's going to give me 36 minus 28, which is equal to 8, which is not 0, which means that x equals 1 is not a root of that equation. So if we're sticking with factors, let's try maybe x equals 3. So again, I'm going to sub it in here. Minus 9, okay, and again we can work out all those values, and if we work that out, sub it into our calculator, we get an answer of 0, as we expected, okay, as we've been looking for, I suppose. So let me see, have I got a calculator here? Let's just work that one through. So what we could do is kind of set up the equation for ourselves here. So that's going to be squared, this one is cubed, just to really kind of take us through the whole process. Let's set this up, and minus 9. So we could start by trying 1 like we did here in our trial and error, and we get an answer of 8 as we got ourselves. And then I'm saying we might try 3, so let's just fill that into our calculator. It's always good to show this first line like I've done on the workings, but then you could put it into your calculator, and here we get an answer of 0. So we know that that means that x equals 3 is a root. And from my factor theorem, so by the factor theorem, that means that x minus 3 is a factor. So if x equals 3 is a root, then x minus 3 is a factor. So once we have a factor, we can divide that in to my expression, because remember that a factor should divide in evenly into my given polynomial. If it is a factor, it should divide in evenly. It's kind of the key definition of a factor, if you like. So 3x squared here gives me 3x cubed minus 9x squared. Then I'm going to be subtracting, so I change my signs. So I get minus 10x squared plus 33x minus 10x plus 30x. And again, we're subtracting, so my signs will change there to give me 3x here, minus 9, and I get minus 1 here, or sorry, not minus 1, minus 3, plus 3, 3x minus 9, there we go. And that gives me, again, subtracting there, gives me an answer of 0. So it divides in evenly, leaving me with this quadratic here, which I can then solve to find the other two factors and therefore roots of my quadratic equation there. Okay, so solving that quadratic will give me an answer of 3x minus 1, x minus 3. And if I take those as roots, I get 3x minus 1 equals 0, which means x equals a third, and x minus 3 equals 0, which means x equals 3. So my three roots are x equals a third, x equals 3, and x equals 3. And we also were asked to fully factorize. So factorized, we can just write the brackets. So in fully factorized form, that becomes x minus 3, x minus 3, and 3x minus 1. And if we wanted to, we could just raise the power of the x minus 3 there, just to give us a really clear. So from our work on graphs as well, we know by looking at that polynomial, it has a repeated root at 3, and then it has a distinct root there at a third. Okay, so we can kind of see that from the definition of our polynomial there from our factorization. So just important to kind of show your workings as best you can there, and then working on your division. So we're coming back to our division. If you want to divide using your box method or something like that, you're perfectly free to do that, particularly with these questions where it generally is kind of straightforward division from that point on. Let's look at an exam question here. So this exam question says that x plus 4 is a factor of this polynomial, of this function. So we want to show that q equals minus 5 and then find the three roots of the function. So if x plus 4 is a factor, that's going to mean that x equals minus 4 is a root. It's going to mean that x equals minus 4 is a root. And we know that that means that f of minus 4 should be equal to 0. Because it's a root, when I sub it into my function, I should get an answer of 0. So let's try it. So we sub in minus 4. I get minus 4 cubed plus q times minus 4 squared minus 22 times minus 4 plus 56. Okay, so let's have a look using our calculator here. So minus 4 or negative 4 cubed plus, or let's just work out everything individually, I suppose. So minus 64, 4 squared is 16, so 16q. 22 times 4 is 88, of course, plus 88 and plus 56. And as we know, we're saying that this should be equal to 0. So I'll have 16q on this side. On the other side, if I add up all my numbers, so 88 and 56, take away 64 gives me 80. Okay, it gives me an answer of 80 there. So I'm going to bring that to the other side. I get minus 80, and that means that q is equal to minus 5, as expected. So we've shown that q equals minus 5. That is going to give me one of the kind of variables there in my question, or one of the kind of unknowns in my question, which means that I can now write it out in full. I'm looking to find the three roots. I already know one of the roots, so I only have to find the other two. And in order to do that, I'm going to divide in the one factor that I do know, subbing in for q as well to allow me to complete that division. And once we get to this point, we're just dividing in the same way we did with the first example there, and the same way as we've done with any of our division previously. So following your usual steps, minus 9x squared, just watching out for any potential hiccups along the way. Minus 36x, again changing my signs, is going to give me 14x plus 56 plus 14, and I get 14x plus 56, and I get an answer of 0. Okay, so I get a nice little quadratic here, x squared minus 9x plus 14. We can solve this, so we're looking for two numbers that multiply to give me 14, add to give me 9, so obviously x minus 7, x minus 2, which means that my two roots are 7 and 2. So overall, my three roots are x equals minus 4, x equals 2, and x equals 7. as my 3 roots there. Okay, so important as well when the question asks you to find the 3 roots, write out those 3 roots at the end. Show off that you've worked out those 3 roots and that you've followed your question through. And you want to be kind of giving yourself every opportunity to kind of gain your marks there. You don't want to have it that you didn't get your marks because you didn't answer out the question fully. Okay, the next question, again, similar to the examples we've done already, it says that this polynomial, this function, has 3 integer roots. Find the 3 roots. So it's one of the questions where we're not given one of the roots to work with, so we have to start by trial and error. So starting by trial and error, again, as per, we're going to take some factors of the constant term here and start with those factors. 1 is always a good place to start. Let's jump straight into our calculator here and set up my question. I'm going to use 1 as my first number for my trial and error. And I get straight away an answer of 0. So when x is equal to 1, f of 1 is equal to 0. So nice and easy. A lot of the time you will find that with these questions. So that means that x minus 1 is a factor. Okay, this is kind of the key part where we're using our factor theorem. This part here is your factor theorem, showing that x minus 1 is a factor. Okay, that kind of distinction between when I sub in the root and I get 0, that means it is a root, that means that this is a factor. And that's really important that you know, and it's always good to show those steps out, show that thinking. So we have that that's a factor. Now that we know that's a factor, we're just going to be dividing into the given polynomial. Minus 5x plus 6, okay, and then the division, honestly, you're just going the same as before. So we're getting lots of practice of our division here, which is no harm, because the division can be something that people find a bit tricky, so it's no harm to just get that bit of extra practice of it. Make sure I don't make any mistakes on it here as well. So minus 6x plus 6, and I multiply by minus 6, I get minus 6x plus 6, and again my signs, and I get a remainder of 0. I can take my quadratic over here. If I'm solving that quadratic, I get x minus 3, x plus 2, which gives me that x equals 3, x equals minus 2. So therefore my 3 roots are x equals minus 2, x equals 1, and x equals 3. Okay, my 3 roots there, nicely worked out for us. The next part of the question says find a cubic equation whose roots are 1 less than the roots of f. So if I look at the roots of f, I'm just going to go 1 less. So 1 less than minus 2 would be minus 3, 1 less than 1 would be 0, and 1 less than 3 would be 2. Okay, taking those roots, I can rewrite them as factors. So x plus 3, x, just x, and then x minus 2. So these are my 3 factors here. If I take those 3 factors, I'm going to multiply those by each other in order to expand this cubic equation. I'm just asked to find a cubic equation, not any specific cubic equation, just a cubic equation that would have these roots. So I'm going to start by multiplying out my 2 brackets here. So x squared minus x minus 6, as we know already, and that gives me x cubed minus x squared minus 6x. And that is a potential cubic that would share the same roots 1 less than the roots of f there. Let's just look at the last question here. Okay, again, it's a lot of the same really that we're working with. They did push you a little bit further with this question. So solve the equation leaving any irrational solution in the form a plus b root c. That is telling me immediately that at some point I'm going to have to use my quadratic formula, my minus b formula, because I know that if I'm looking for solutions, my solutions should be roots of my equation. So that's telling me some of the roots are going to be irrational. I need to use my minus b formula. So starting off the same as always, we're going to try our trial and error. We can try where x is equal to 1. So let's just manipulate what I have on the calculator here to save us a little bit of time. Minus 9 and plus 11 at the end here. And I get an answer of 0. So when x is equal to 1, f of 1 is equal to 0. Okay, just showing, and it's good to show you writing that out as well. So I would show that you've subbed in 1. Sometimes in these ones, particularly if you can't come across the answer, it's good to show yourself subbing into a few options so that you're really driving home that you're using that trial and error. But we know now that when x is 1, that is a solution, which means x minus 1 is a factor. So same as before, I'm going to divide that in. Okay, and x squared, so x cubed minus x squared. Again, change my signs. So minus 2x squared plus 2x. Change my signs. So minus 11x plus 11, and I'm going to get minus 11 here. And I then get a remainder of 0. So I'll have a nice quadratic there, x squared minus 2x minus 11. I'm not going to even waste any time looking for potential guide number matches or anything like that, because I know I should have irrational solutions. I haven't come across any yet, so I'm thinking that means there's going to be some within this question here. So let's just go looking. So 2 times 1, so filling into our quadratic formula as per normal. 4 plus 44 over 2. So x equals 2 plus or minus the square root of 48 over 2, which if I reduce that down gives me 1 plus or minus 2 root 3, reducing that down. So that gives me my 3 roots as 1 plus 2 root 3. So let me just write x equals 2. X equals 1 plus 2 root 3, x equals 1 minus 2 root 3, and then as we had before, x equals 1. Nice and straightforward. So again, just writing my roots out at the end there. So the key thing with the factor theorem really is that initial statement of the theorem, and as I said, it's really focusing in some ways on this part. If we have a root, then this is a factor, and a factor will divide in evenly. So we're really using all of that information to help us with the question. There are maybe some other types of question you could be asked, or questions we came across in the book or in class, where maybe we end up with some different things, or where we have to make use of the factor theorem in order to maybe find different constants. We saw that a little bit in this second example here, or not the example, sorry, the exam question, where we're looking to show that q is equal to minus 5. So it's important that you know as well that when you sub a root in, that you get an answer of 0. So if you're given a factor, that you can twist that to a root and sub it in to get an answer of 0. So there is, obviously, it's important you know both sides of the theorem. We just happened to use that second, or the converse of the theorem, a lot more in these questions than we did perhaps the first side. But really both work together, both are important to know. So definitely an important theorem to know, and particularly one to look to if you're asked to solve or factorize a cubic equation, or anything higher than a cubic equation.